Okay, good evening. My name is Mr. David Glante. For those of you who may not have known me, I've been teaching some students in grade 10 and 11. Perhaps you were one of those students, but if you are new here, you are welcome. Today's lesson is going to be on matter and materials, grade 12. This is, I think, the most important topic as far as chemistry is concerned. The reason being that for every paper two paper, usually there are three questions that are asked about organic chemistry. And I just checked one of the papers now. The total marks for all the three question papers combined is about 44 marks. So that is huge. That is massive. And so if you want to pass your metric, this is a topic that you cannot avoid. So I would encourage you to listen and listen attentively. Fortunately, I've tried to simplify it. I've invested a lot of energy. Usually, I don't do so much in terms of, making it very useful. But of course, I want you to perform because you're paying money and you should have something good. So let's go straight to the point. What is organic chemistry and what are organic molecules? Now, organic chemistry is simply the study of carbon and its compounds with the exception of carbon dioxide, carbon monoxide, carbonates, hydrogen carbonates, cyanide, and all allotropes of carbon. So, so that is organic chemistry, is the study of. But when you are defining an organic molecule, you say an organic molecules, they are carbon-containing molecules, with the exception of carbon dioxide. Let me change the color of this thing so that let me change this color. Okay, so let's go back. Yeah, so I'm saying that organic molecules are carbon-containing molecules with the exception of carbon dioxide, carbon monoxide here, carbonates, hydrogen carbonates, and cyanide. Let's even forget these allotropes because allotropes are not actually compounds. Okay. So it means that any other substance that contains carbon is an organic compound. Okay. So we can rephrase this or paraphrase it by saying that all organic molecules, organic compounds contain carbon, but not all carbon containing compounds are organic compounds. I hope this makes sense. But as we go on, these things will be made clearer. Now, it's also important to understand that these organic molecules can be gases, they can be liquids, they can be solids. It doesn't have to be, it occupies all the three states of matter, solids, liquids, and gases. And then the last thing I want to mention is that all living materials contain organic compounds. Everything that is living has organic compounds. So now we're going to look at what we call the uniqueness of carbon. What makes carbon so special that a whole aspect of chemistry is devoted to it? So we're going to look at it. The first one is that carbon is in group 14 according of the periodic table of the periodic table in the old system of the old periodic table, they'll say it's in group 4 like this, but these days they have changed, so let's use the changed one, which is group 14. The next thing about carbon that is important is the fact that carbon has a valency of 4. It means that the outermost shell of carbon contains 4 electrons. So let me draw it here so that you see what I'm talking about. When you refer to the periodic table, you will see that the atomic number of carbon is 6. So carbon is 6 here. If you draw the structure, you have the nucleus here. The first shell here takes 2 electrons, and the rest go into that. 1, 2, 3, 4. Now, the valency is usually the combining power of an atom. In other words, the number of electrons that are used in chemical bonding. So this can participate in a chemical bond this can participate in a chemical bond, this and that. In fact, all four of them participate in chemical bonding. I'm talking about covalent bonding, which you did in both grade 10 and grade 11. So we say it has a valency of 4 because of these electrons in the outermost shell. Okay, so let's continue. Now, because of the ability to form bonds, these bonds can be single bonds, they can be double bonds or triple bonds. It's not only single bonds. We'll see them as we proceed. And the ability of carbon to form long chains of carbon with other carbon atoms is called catenation. Catenation. Okay. So now let's look at the types of carbon atoms that you would encounter in organic chemistry. The first one is what we call primary carbon atoms. Okay, primary. A primary carbon atom is a carbon atom that is bonded to another carbon atom. So if you look at this one like this, it's a primary carbon atom because it's bonded to another carbon atom. Okay, one carbon atom bonded to another carbon atom. We say it is a primary carbon. So this is primary. And this is also a primary carbon atom. The rest are hydrogen atoms, depending on, forget about this. Okay, the rest are hydrogen atoms. Now let's move to secondary carbon atom. In a secondary carbon atom, you typically have one carbon atom bonded to two other carbon atoms. So you have one carbon atom, this central atom here, this one, is bonded to one here, is bonded to another one like this. So the presence of these two carbon atoms bonding to or attached to the central one makes the central one a secondary carbon atom. Then we come to what we call a tertiary carbon atom. In a tertiary carbon atom, you are going to have one carbon atom bonded to three carbon atoms. So this is the first carbon atom, this is the second carbon atom, this is the third carbon. All of them are attached to this carbon. So this one is called a tertiary carbon atom. And then, of course, there's what we call a quaternary carbon atom. And this is an example. You have the central carbon atom bonded to four other carbon atoms. You have this one here, this one here, this one here, and that one here. So there are four. We call them quaternary carbon atom. This is like that. Okay. So that is that. Now, if you have a substance or a molecule like this, okay, this is called methane. We will look at it very soon. It's an example of an alkane. This one is not, it's neither primary, secondary, or tertiary, or quaternary because it's only one carbon atom. It's not bonded to any other carbon. So it doesn't fall under this classification. We exclude this. So let me quickly add that you don't really have to bother yourself about remembering this. This will become useful when we talk about alcohols. Alcohol is one of the, organic molecules that we'll be looking at. That's when this whole idea would be necessary. But until then, it's not important. So apart from carbon, you also have a number of elements that are attached to carbon. In the examples that I gave previously, you'll see that hydrogen is one of them. Now, hydrogen is attached or has the ability to attach to only one covalent bond. In other words, hydrogen is drawn like this, and it is attached by only one covalent bond. Okay, hydrogen, a covalent bond like that. Then another one that you should be familiar with is oxygen. In the case of oxygen, we have double bonds. So the double bond can be in this way, okay, as in the case of, let's say we have something like this. You can have something like this carbon, and then you have oxygen. So you see that there are double bonds here associated with this one. And then maybe you have something like this for the carbon, okay? Or you can also have it like this, bonded to maybe a hydrogen, and then bonded to something else, maybe a carbon. So you see that the bonds are on opposite sides. They are not like an equal sign. So irrespective of the shape, we will look at how these things are written as we go on. But irrespective of the shape, just know that carbon uses two covalent bonds, okay? I mean, not carbon, oxygen. The element oxygen has to have two covalent bonds attached to it. So that's important. Then we also have halogens. The halogens are group, what we call group 7 or 17. You have your fluorine, your chlorine, your bromine, and your iodine. All of them are called halogens, and they can also be attached to a carbon atom. We'll look at them in details later on. Now, before we go, we need to be familiar with certain terminologies, okay? Terminologies that you come across, terminologies that I'll be using frequently. And there's always a tendency of not knowing what it is, because at that time or when I begin to use them, I assume that you are familiar with them. So we have the first terminology is what we call a hydrocarbon. Now, a hydrocarbon is an organic compound or an organic molecule that contains carbon and hydrogen only. Carbon and hydrogen only. So the hydro stands for hydrogen, and of course, the carbon is a carbon. So all hydrocarbons contain only carbon and hydrogen. Now, hydrocarbons can be of two types. We have what we call saturated and unsaturated. We'll look at them in detail as we proceed. These are terminologies that you should just be familiar with. But when you talk about saturated hydrocarbon, you are saying it is a hydrocarbon that has only single carbon-carbon bonds. So let's say we draw something like this. Uh, okay. This carbon-carbon bond is single. It's not a double line. It's one line, one straight line like that unites or attaches these two carbon atoms. So the presence of this one makes it saturated. Saturated. Uh, you will see the implication at a later stage when we look at reactions of alkenes, alkynes, and so on and so forth. But these are called saturated, only single bonds. Then we have what we call unsaturated hydrocarbons. Now, the unsaturated ones can be double bonds or triple bonds. That is alkenes or alkynes. Let's take note of that. So let me just show you this so that you see what I'm talking about. The presence of a single bond here, this is a single bond, so it's called an alkene and it is saturated. Now, if it is unsaturated, it might be a double bond or a triple bond. The double bond is what you see here, two lines. We call that a double bond. And then we have three lines here called triple bonds. Okay, we'll look at each one of them. Some of these things you have to ignore them because I took them from some books, so sometimes I forgot to clean them. I cropped them, so sometimes I'm unable to crop them. Okay, now we're going to look at ways to represent organic molecules. There are a number of ways that we represent organic molecules. The first one is what we call a general formula or a general molecular formula. Now, the general molecular formula is normally used to, it's a formula that many groups of or many organic molecules conform to. In other words, they have the same general formula. I'll be using it at a later stage, and then you see what I mean by a general formula. So because it's called a general formula, an example of this is C2, yeah, H2N plus 2. Now, in mathematics, when you see N and then X, you know that they are variables that can mean any number, 1, 2, 3, 4, 5, like that. So we will see how to use this very soon. Then we have what we call empirical formula. Now, in grade 10 and in grade 11, your teacher must have taught you about empirical formula and molecular formula. So when you talk about the empirical formula, you are basically saying it is the simplest whole number ratio of atoms in the molecule. So this is an example of an empirical formula. And then the molecular formula is the actual, shows the actual number of atoms in a particular molecule or compound. So in the case of this, you have carbon and hydrogen, and this is that. Okay. Now, if you look at this, let me bring this one here for those of you who perhaps are joining recently, perhaps I didn't teach you this in grade 11, but the grade 11 students were taught this. So let's say this is the molecular formula. If you divide this by 2 and divide this by 2, this one cancels that, and this one gives you 3. So you're going to have CH3. That's what we mean by the simplest ratio. So whereas this is called the empirical formula, this is the molecular formula of this empirical formula. But the good news is that in organic chemistry, we don't do much about, we don't really talk about empirical formula. It's usually molecular formula, structural formula, and condensed structural formula. So let's move to what a structural formula is. Now, a structural formula is a formula that shows all the bonds and atoms in a molecule. So if you look at this, you have a carbon here, another carbon here, and all the bonds, the covalent bonds, are indicated by straight lines. All these ones are covalent bonds. So when you draw something like this, we say it is the structural formula. It is the structural formula. Okay? Structural formula. Then we have what we call condensed structural formula. With the condensed structural formula, you include some bonds and you ignore some bonds. So for this same structure here, we have a carbon here and 3 hydrogens. So we write carbon and 3 hydrogens. And then for this one, we also have a carbon and 3 hydrogens. So another carbon and 3 hydrogens. So when you write it like this, we call it a condensed. Condensed means you make it smaller, compact. So this is a condensed structural formula. You can write it like this, or sometimes you can also indicate the bond between them. Actually, you can do it like this, or perhaps better still, you can do it like this and then like this. Now, this thing is the same thing as that one. The only difference is that we brought the hydrogen backwards and then left the carbon there because the bond is between one carbon and the other. So this is a better way of representing it. But of course, if you write it like this, nobody cares. I mean, people know that it is used in everywhere. So you shouldn't have a problem. But my concern is where learners suddenly see something like this, instead of starting with carbon, they see a hydrogen and then they start panicking. What is this? It's just a matter of position, changing the position so that you're able to establish that the bond is between one carbon and the other, something like that. Okay. Then we move to a functional group. A functional group is an atom, a group of atoms, or a bond that determines the physical and chemical properties of organic molecules. Now, there are thousands and thousands, perhaps millions of organic molecules. However, uh, there is always a relationship between one and the other, at least some of them. In other words, some in a particular group will show certain characteristics. So those characteristics are determined by the type of bonds they have, or if they have a certain uh, atom that is attached to them or group of atoms. It makes them have certain specific physical and chemical properties. So let me give you a more practical example so that it doesn't look theory. Let's say you live in a place, a big place, and there are 5 schools there. You would realize that the learners in the 5 schools wear different uniforms. So when you see a learner in maybe black, you know that the learner comes from school A. If they are in blue or pink or what, you know their school. So that's how a functional group is. It's something that makes you identify a group of molecules. Okay, so we'll talk about that. Then we have what we also call a homologous series. Now, a homologous series is a group of compounds that have the same general formula, and then each one of them differs from the next by this. So on the basis of that, we are supposed to learn 9 homologous series. The first group are called alkanes. Then we have alkenes. Then we have alkynes. Then we have alkyl halides. Then we have alcohols. It's a bit different from what you drink at home if you drink alcohol. I hope you don't. But then we'll see. Alcohol, the term alcohol is much broader than the one people drink. So we call them alcohols or alkanols. Then we are going to look at aldehydes. Aldehydes, look at ketones, carboxylic acids, and esters. These are all homologous series. They are like different schools in a particular area. And each of the school has a specific uniform. The uniform is called the functional group, something that makes you identify that this molecule belongs to this group or this homologous series. So that is it. Now we are going to look at each one of them briefly. We would always be going back and forth. We'll start with an overview of each one of them. Having finished the overview, then we'll begin to look at how to name them. We'll go through all the names, and then we'll look at how they react, the chemical properties of each one of them. That's why I said this topic is huge, and so you should take note of that. So we are going to start with alkenes. This is an overview. When I say an overview, it means I'm just going to touch it briefly, just to give you an idea what it is. Then we'll delve into each one of them later. Today, I'm hoping that we'll start with alkenes by looking at even how to name alkenes. So I'm going to go through all the homologous series, just give you information. Don't worry about it. Just try to see whether you can remember any of them. But then we'll go into specifics. Each one of them will learn how to name them and so on and so forth. So we start with alkenes. Now, alkenes have single bonds between carbon atoms. So we say they are saturated hydrocarbons. Okay? Saturated hydrocarbons. The functional group is what makes you identify an alkene is a carbon-carbon single bond. Okay, single covalent bond. They have a special name. Their names end in ane, A-N-E. So whatever you have, it must end in A-N-E. And they have what you call a general formula. This is the general formula of alkanes. Now, anybody who teaches organic chemistry will tell you that usually when you're teaching organic chemistry, you have to put in a lot of emphasis on alkanes, because if you understand alkanes, the other ones will be easier to understand. So I'm going to spend a lot of time. I'm going to break down things, and it might look long. This lesson might be long, but bear with me because I want to lay a good foundation for you. So we are going to look at what we call the list of, according to the syllabus, you should learn the first 8 members of the homologous series. So the first one has carbon number 1. I mean, has only one carbon atom. And if an alkane has only one carbon atom, we call it a methane. You see, I said the names end in ane. So it's a meth and ane. So this is methane. Then if there are 2 carbon atoms, we call them ethane. Also ends with that one. If there are 3 carbon atoms, it's a propane. Also like that, ends with an ane. Then 4 carbon atoms, butane or butane. Then 5 carbon atoms, pentane. 6 carbon atoms, hexane. 7 carbon atoms, heptane. And then 8 carbon atoms, octane. Now we are going to look at what we call the molecular formula. I've written a lot of stuff here. You might be confused. How did he get all these things? So we are going to use the general formula here to see how to write these things. I'm going to do maybe a couple of them and then we'll see. So the general formula is CnH2n plus 2. So if your if your molecule has only one carbon atom, you are going to have C, and then here you put 1, then H2 times 1 plus 2. So this gives you C, and then H2 times 1 is 2 plus 2 is 4. 4. So that's how we got this formula here. CH4. So CH4 is called methane. Okay? CH4 is called methane. Let's go to the second one here. Ethane. The number of carbon atoms in ethane is 2. So we're going to write C2, then H2, the N is also 2 times 2 plus 2. So what I mean is that for ethane, N is equal to 2. So the 2 comes here. Then the other 2 is 2N. So that is the 2 here. And then plus that. So this is going to be C2. Then the H is 2 times 2 is 4 plus 2, 6. That's how you got this one, this formula like that. Okay. Like that. Then I'm going to end at 4. Then let's do the third one, which is propane. Let me see something. Yeah. So with propane, we're still going to use the general formula CnH2n plus 2. Your N, which is the number of carbon atoms, is 3. Okay? So you're going to have C3, then H2 times 3 plus 2. So we're going to have C3H, 2 times 3 is 6, plus 2. So this is 8. So that's why you have this one there, C3H8. Okay? And then we'll just finish with the fourth one. I don't want us to waste a lot of time. The fourth one is butane or butane. So that one, the value of N, which is the number of carbon atoms, is 4. So you're going to have C4H2 times 4 plus 2. So this gives us C4H, 2 times 4 is 8 plus 2, 10. So you have that. So C4H10. So that is what you have here. Okay, that is what you have here, C4H10. So you do that and up to 8, and then you get that. Now you will see that in addition to that, those ones that I have circled, these ones that I have circled are called the molecular formula. These are the molecular formula or formulae. Molecular formula. These are the molecular formula. Then the condensed structural formula are these. So let me show you how I got this. So with respect to this, let's use that one alone. This is C2H6, okay? And this is called ethene, or ethane, sorry, not ethene, ethane, ane, the end in ane, like that, okay? So I'm going to show you how I got this one. So because there are 2 carbon atoms here, you draw it like this, a carbon and another carbon. Now, this is a hydrocarbon, and we have also established that each carbon atom takes 4 bonds. So you simply attach 4 bonds to it like this, like that. So this is 1, 2, 3, 4. This is 1, 2, 3, 4, because it has a valency of 4. 4 electrons in the outermost shell, if you recall the example I gave you. So you need to form 4 covalent bonds. So every carbon atom must be surrounded by 4 bonds. So with this one, you will write a carbon, we call it the carbon skeleton. This carbon like this, and then another carbon. Okay, it's 1 bond like this. Then the rest, you just surround them with hydrogens. Hydrogen, 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 hydrogen. So when you finish that, this is called the structural formula. This is the structural formula that is obtained from the molecular formula. This is the structural formula. Now, having obtained the structural formula, you can now condense it. Condense means you make it smaller. So you take a carbon like this, and then you count the number of hydrogens around the carbon. There are 3. 1, 2, 3. So you write H3. Then you go to the next carbon. You write it like this, and then you count the number of hydrogens. 1, 2, 3. So this one also becomes CH3. Okay? So you can write like that. Sometimes, so you can also, like I indicated before, instead of writing it like this, you can bring this H backwards. So it becomes H3 carbon and then another carbon CH3. You do this to show that the bond is between carbon and carbon, not hydrogen and another carbon. So sometimes they write it like this, and when you see, don't get confused. It's basically the same thing. Okay? So you do that, and you'll be able to get all these ones. Okay, so let me talk about propane, and let's see how we do it. Let me talk about propane. Propane is 6, 3H8. So the structural formula will be C1, 2, 3. There are three of them. Then we simply put hydrogens like that, like that, like that. So this is hydrogen, 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 hydrogen. So if you count the number of carbon atoms, it's 1, 2, 3. That is 3 here. Hydrogen atoms, this is 1, 2, 3, 4, 5, 6, 7, 8. That's why you have something like that. So if you want to condense it to make it smaller, you start from this side. This is your carbon. You can write it as carbon like this, and there are 3 hydrogens, H3. Then you go to the next carbon, it has 2. So write carbon and 2 hydrogens. Then you go to the next carbon, it has 3. So you write it like this. Okay? Or if you want, you can take this one backwards instead of writing it here. You can also put this one at the back like this and then write it like that. You can also put even this one at the back you don't put it like this. I think you just leave it like this. So with respect to this one, you can change it like this, but it is acceptable to just write it as CH3, CH2, CH3. So 3, 3, and then the middle one is 2. So you can continue the same thing, and then you have all these things. But sometimes, let's take a look at this one, butane. Butane is C4H10. So this is C3, C2, C2, C3. So because there are two C2s here, this C2 here, and another C2 here. We can write C3 for the first C3, then the C2, because there are two, we put it in brackets and put 2 there, and then C3. That's another way of doing it. If there are 3 C3s, look at the CH2, 1, CH2, 2, CH2, 3. So you say CH3, this first CH3 is this one. Then the CH2, we put it in brackets and put 3, and then that one. Okay. So basically, this is how you do it. And we have an example, set of examples here. That's what I just mentioned. So this is your methane. This is your molecular formula is CH4. And the condensed formula is also CH4. You can't change it into anything different from this. So the structural formula, you expand it, you put your carbon in the center, and then you attach hydrogens to it. So you're going to have something like this in the case of this one. Then ethane, the molecular formula is C2H6. This is the condensed structural formula. And then this is the structural formula, something like that. So this one is like that, this one like that. It's basically the same thing as what I have already given you, this list. The only difference is that there I did not include the structural formula. So these are all the structural formula. You just expand them. Okay, just expand them. So let me even use one of this. Let's try to draw this so that you see what is happening. So it's C5H12. So how do you do it? C5 means there are 5 carbon atoms. So you say 1 carbon, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Then you just attach hydrogens. Wow, like that, like that. This one like this one like that, this one like that. And then, so this is H, 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 H. The reason we do that is that carbon takes 4 bonds. So this carbon is attached to 1, 2, 3, 4. So it is complete. This other carbon is attached to 1, 2, 3, 4. So it's complete. This one is attached to 1, 2, 3, 4. This one is attached to 1, 2, 3, 4. 1, 2, 3, 4. Every carbon should have 4 bonds, 4 covalent bonds attached to it, and hydrogen should have one. So if you look at this, you see that there are 1, 2, 3, 4, 5. So that is your C5, and your hydrogens start with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So C5H12. That is how we go about it. Okay. So this is very important. This is very important. Now we are going to look at what we call alkyl groups. So far, we have looked at alkanes, and we are going to proceed by looking at what we call alkyl groups. Just hold on a second. The electricity is gone off. I want to connect something here. Okay, I'm back. It's a problem of electricity, so I have a, what do you call it, an inverter. So I connected it. Okay, so let's proceed. Now we're going to talk about what we call alkyl groups. Now, the alkyl groups are normally represented by R. We'll see the application of this written as R, or sometimes they'll write it R and put something like this, just to make a distinction. Now, what are alkyl groups? Now, an alkyl group is simply an alkane that has lost one hydrogen atom. So we have something like this. You have an alkene like this. If you subtract, this is minus hydrogen. Whatever you are left with is called an alkyl group. Okay? An alkyl group. Now, these are given special names. Instead of the name of an alkane ending in ANE, these ones, they end in YL. Okay, so let me give you an example. So if you have an alkene like this is called methane. Methane. If you remove a hydrogen there, we have a partial structure here. It is still a meth, but it ends with I, methyl. Okay? These are called substituents or side chains. We'll talk about them later when we look at how to name alkanes. Okay? So we have that. Now, this alkyl group, which is a substituent, usually is represented by the symbol R, can replace hydrogen in a structure. So look at something like this. This is a methane. This is a full methane here. Okay. If you remove this hydrogen here, the hydrogen has to be replaced. You can replace the hydrogen by attaching this. This is an alkyl group, which is a substituent, or you can put R there, but usually R is generic. There are so many alkyl groups. Any alkane that you remove one hydrogen out of it becomes an alkyl group. So it is always important to, sometimes for purposes of convenience, they just put R there. We'll see what I'm talking about later. But in the absence of that, it's always good to put what is exactly there. So what I'm saying that instead of having an alkane with this one, you can remove this one and replace it with something like this. This is an alkyl group. We'll see it with subsequent examples. Okay, so there are so many alkyl groups, but according to the syllabus, you're supposed to learn only two. You are going to learn about the methyl and ethyl group. Remember, I said it's methane. You remove one hydrogen atom out of it, and then it becomes a methyl. So that's why you have this. Instead of CH4, it's now CH3. So you write it like this. And I said you can put the H backwards like this. So this is the condensed structure. This is also the molecular structure. And then this is the structural formula. So you write it there. Instead of putting a hydrogen here, you leave it without the hydrogen. Okay, this is attached, would be attached to something at a later stage. So this is a methyl group. Then this is an ethyl group. Again, this is ethene. This is supposed to be CH3, CH3. So if you remove one hydrogen, it's CH3, CH2. That's why you have this. You can also combine the carbons because there are two carbons here. You can combine them and write C2, and then you also combine the hydrogens. Here you're going to have 2 plus 3, 5. So when you see it like this, they are the same things. Okay, either you write CH3, CH2, or you write C2H5. They are all ethyl groups. And this is how you write the structure. You leave the hydrogen here, this hydrogen here out. You just leave it like that. Okay. So we have finished with alkanes. We are now moving to alkenes. Now, alkenes are unsaturated hydrocarbons, but alkenes, they also contain saturated bonds, but you don't use them. So let me give you an example. Let's say we have a certain bond like this. Okay. Let me use this as an example. We'll draw a lot of them later, and then you see what I'm talking about. Okay. So you can see that the carbon-carbon atom, I mean, the carbon-carbon bond here between this one and this one is a single bond. Between this and this is a double bond. Okay. So even though there are single bonds and double bonds, the double bond is what we use to identify this. So the presence of a carbon-carbon double bond makes the molecule an alkene. See the spelling, alkene. What we did before was alkane. This is alkene, E-N-E. So this is the difference. So we're dealing with alkenes here now. They are double bonds and their names end in, and this is the general formula. There are also examples of what we call unsaturated hydrocarbons. So we do the same thing. We are supposed to know the first 8 of them. But when it comes to alkenes, the first member doesn't exist. You don't have methane. The word, I mean, the molecule methane doesn't exist because we're talking about a carbon double bond. So there has to be a double bond between one carbon and atom and the other. So they have to always start with 2. So methane doesn't exist. So carbon number 1, there is nothing. Carbon number 2 is ethene. So remember I said the general formula is CnH2n. So if the carbon atom is 2, you're going to have C2, and then the H is 2 times 2, 2 times 2. So you're going to have C2H4, okay? Then C3 will be 2 times 3, so it becomes C3H6, C4H10, C5, like that. So these are all the members, like the previous one. However, their names end in. So this is ethene, propene, butene, pentene, hexene, heptene, and octene. So the same way we went about the previous ones, the same thing applies here, except that I want to show you something. We'll come to naming of organic compounds, each one of them. I'm going to go through each one of them. So you'll see in detail how these things operate. But let me take this one, ethene. So this is a theme, and then show you how to draw it. So you write a carbon atom here, and then a double bond, another carbon atom. So you can draw them like this, like that, like this, like that. So you can put it like this, like this, like this, like this. Okay? Or you can also have them drawn like this. Can have just carbon, carbon, a double bond, carbon. Excuse me, let me, yeah. Then you draw a hydrogen here, another hydrogen here, and then a hydrogen here, and then another hydrogen here. So this is another way of drawing the same thing. Okay, you see that this one is a bit different. The drawing is different. It's just a matter of choice. So you can draw it like this one, like this. The most important thing is that each carbon must have 4 covalent bonds. So this carbon one has 1, 2, 3, 4. This one also has 1, 2, 3, 4. And all the hydrogens have 1, 1, 1, 1, each one of them. So you can also draw it like this. In other books, you also see them drawn like this, C, like this, C, and then they will do it like this, hydrogen, put a hydrogen here, put another hydrogen here, and then put a hydrogen here. So it doesn't matter how you see it. The most important thing is to look for the double bond and make sure that every carbon is surrounded by 4 covalent bonds, and then every hydrogen is surrounded by 1 covalent bond or attached to it. So you have that. This is something I just took from the internet. It's just the same thing. These are your molecular formulas. And then with your condensed structures, you can put a double bond here, or you can just leave it as CH2, CH2. So this is another way of doing it, but then attach it to the first carbon. We'll talk about naming, and then you see that depending on where this is attached, the name will be different. That's why there are thousands and perhaps millions of organic molecules. You can just change the positions of the double bond and you have a different compound altogether. So we have that. Yeah, so yeah, this is basically the same thing. It's another way of representing it, like I indicated. So this is your ethene. This is your propene. You see, this one, the double bond has been placed here. The double bond has been placed here. You can also write it like this. You can start a double bond on this side, on this side. So you can also have C here with a double bond, then another C, then this one, okay? And then you have your hydrogens here, hydrogen, hydrogen, hydrogen. Then here there is only one hydrogen. And here there are 2 hydrogens, like that. So it's like turning this upside down. You take this one and bring it here, and take this one and bring it that you are flipping them. So it doesn't matter whether the double bond is on this side, on the left-hand side or the right-hand side, as long as it's at the beginning. We'll talk about naming and then you see what I'm talking about. So you have the whole list like that and you just go through it. These are all the structural formula of these alkenes, okay? Then we go to alkynes, alkynes, alkynes. Remember, we started with alkane. Then we went to alkene, E-N-E. Now we're going to talk about alkynes. Now, oh, and let me continue with this. Let me go back to this quickly. Now, even though these ones, we only see single bond, one double bond. You can have more than one double bond here. You see, here is just one double bond, okay? Even if there are 2 double bonds somewhere, maybe a structure like this. Let's say you have something like this, something like this, then you have something like this, maybe something like this. Okay, this is your H, this is H, this is your H here, This is your H here. Don't worry, we'll see a lot of examples so that you see what I'm talking about. This one is like this, and then this is H, this is H. So this one has a double bond here and also has another double bond. It's still an alkene. So the presence of one or more double bonds still makes it an alkene, but these ones have a special name. We'll look at them when we deal with writing the names of organic molecules. But for now, just take it like that. So let's quickly go to alkynes. So with respect to the alkynes, the most important thing is their general formula. You use the general formula. Again, there is no first member. The first member doesn't exist. So the bond is a triple bond like this. One, two, three, between the carbon atoms. Okay. The carbon atoms is three double bond line. And then the first member is this. I said there isn't, you can't have one with only one carbon atom. It starts from two. So that's why you have ethyne. Their names end in ine. So this is ethyne, propyne, butane, pentyne, hexyne, heptyne, and octyne. And then all these are the same things that I did before. I use the formula, the general formula, and with the general formula, I get I'm able to establish the structural formula and the molecular formula. We did that, so I wouldn't waste my time on this. So or maybe if you're interested, you might be keen. Okay, so let's draw the first member. We said the formula is CnH2n minus 2. So we said the first member, carbon number 1 doesn't exist. So we start from carbon number 2. So it's C2 and then H2 times 2 minus 2. So it's C2H2. So if you're drawing it, you're going to have carbon, and then there are going to be 3 bonds. That is a triple bond. And then you attach a hydrogen here. You attach another hydrogen here. Okay? Or you can write it as, so this is the structural formula, or you can write it as like this C, and then you put your H like this, and then you also put your C and H like this, okay? This is the condensed formula. So you do that for each one of them, and that is what you are going to have. So this is an example. I thought I had an example here. Oh, okay. So this is an example of what we are talking about. So this is the structure of, forget about this, this prefix and suffix. This is called ethyne, propyne, butane, pentyne, hexyne, heptyne, octyne, all ine. So this is the first member, the one that I showed you. Ethyne is drawn like this. Then the other members, you just put the double bond towards, the triple bond towards the first carbon atom. So you have that. We'll talk about naming of these compounds so it will become clear. But for now, just have an idea about how these molecules look like. You have that. Then let's talk briefly about what we call haloalkanes. Haloalkanes. Now, haloalkanes have other names. Sometimes we call them alkyl halides. Now, a haloalkane is simply an alkane in which a hydrogen has been replaced by a halogen. Okay? So they have this general formula here, like this. So let me give you an example. This is methane. This is methane. This is methane. Now, if one of these hydrogens, if we get rid of this hydrogen and replace it with, let's say, chloride, you're going to have C, and then you're going to have H, another H here, and then here we'll put Cl. The Cl is taking the place of this one. So because of the presence of a halogen, either fluorine, chlorine, bromine, or iodine, we don't call this an alkane any longer, but a haloalkane. The halo comes from halogen, and the halogens are fluorine, chlorine, bromine, and iodine. So when we attach this, we have that. Now, because there are so many types, I don't want to go into this. What you'll be required to do is to learn how to name them, and we'll come at a later stage, we'll talk about the naming of these molecules, and you'll see what I'm talking about. So we have that. Then we move to the next functional group. This functional group is called alcohols or alkanols. Okay, alcohols or alkanols. Now, the alcohols have a particular functional group called the hydroxyl functional group, not hydroxide, but hydroxyl. And this is what you have there. And their names end in all. Ethanol. The alcohol you eat at home is called, you drink is called ethanol if you're a drunkard, but I don't think you drink. So it's called ethanol. It comes from ethane, but instead of ending with ethane, you replace the E and add OL. We'll talk about how to name them later, and they have a general formula like this. Then we are going to look at the types of alcohols. We also have, just like the types of carbon, we have primary, secondary, and tertiary. In the primary, your OH is attached to the first carbon atom, which is also attached to one carbon atom. Okay? So instead of having it like this, you can also have it like this. Let's say three, let me put this ones like this. So this OH, instead of placing it here, you can place hydrogen here and rather place it OH. It's still on carbon number 1. This is the first carbon. So whether you place it here, you place it here, or you place it here, it is still the same as this. So this is equal to this. These ones are the same things like that, like this, like this. Okay? So we've just changed the position spatially, but they are still attached to carbon number 1. So this one is the same thing as this one. And it is attached to a carbon that is also attached to another carbon. So we say it is a primary alcohol. Then we go to a secondary alcohol. In the secondary alcohol, you have your OH here. You can also place it here. But then it is attached to a carbon atom that has two that are attached to two other carbon atoms, like we did before. So this is a secondary alcohol. And then we have a tertiary alcohol. In the tertiary alcohol, you have the OH hydroxyl group attached to a carbon that is attached to 3 other carbons. So this is the first carbon, this is another carbon, this is another carbon. So 1, 2, 3 is attached to a carbon that is attached to 3 other carbon atoms. So we refer to this as a tertiary alcohol. We will look at a lot of examples later. Then we have what we call aldehydes and ketones. Aldehydes are also another functional group or a homologous series, and the functional group is the carbonyl group. Their names end in nal. So ethanal, okay? Ethanal, not eating, but ethanal, butanal, pentanal, something like that. So we'll look at all of them in details. Then we also have ketones. Ketones are also another type of carbonyl group, but their names end in none. So you can have something like pentanone, okay, or hexanone, okay, or butanone. So their names end in none. We'll look at each one of them later. Then we have carboxylic acids. The carboxylic acids end in oic. So you say, so this is the functional group. What makes you identify it is this group. Then their names end in oic. So you can say ethanoic acid, okay? Pentanoic acid, oic, like that. And this is the general formula. Then the last one we are going to look at are called esters. And they also have a carbonyl group like this, but they are in this format. Their name end in OATE, O-A-T-E. Like I said, we'll look at them in details because now I don't like combining them. I like to take each one of them and deal with them specifically with a lot of examples so that you'll be able to understand instead of, just combining them all at once. You won't be able to remember. Okay. So this one is just a table of functional groups. What I have written there This is basically it. It's a summary. So for alkanes, this is the functional group. They are single bonds between carbon-carbon atoms. So these single bonds. So we call that an alkane. Alkenes have double bonds. Alkynes have triple bonds. Haloalkanes or alkyl halides, they have X, where your X can be fluorine, chlorine, bromine, iodine. They are called halogens. So in place of the hydrogen, you have X, and X can be any of these things. Then you have alcohols, the presence of OH. Then aldehydes are like this. This is how the functional group looks like. We'll look at each one of them in detail. Then ketones are like this. And then carboxylic acids are like this. And then esters are like this. Okay. So we are done with the overview of all the homologous series, the 9 homologous series of functional groups that we are supposed to study. Now we are going to talk about naming of organic molecules. The naming of organic molecules. Now, the naming of organic molecules is governed by what we call the IUPAC system of nomenclature. IUPAC system of nomenclature. When you say nomenclature, simply means naming. To name something is nomenclature. That's a scientific way of saying naming, nomenclature. Now, IUPAC stands for International Union of Pure and Applied Chemistry. Now, why do we need the IUPAC name for our system for naming organic compound? The reason is simple. There are millions and millions of organic compounds. So if I write the structure of an organic compound here, or I name an organic compound in South Africa and send it by email to someone in Japan or the US, the person must be able to draw the structure, just like I have drawn it in South Africa. So you have to agree to a system. A system means that rules that you follow in naming organic compounds. And then on the basis of that, there is uniformity. It avoids confusion, it avoids ambiguity. Okay? So that's why the IUPAC system of naming is important. Now, according to the IUPAC system of naming, each compound is unique and it has 3 parts. The first part is called the prefix. Then the second part is called the root or the parent name. And the last part is called suffix. So prefix, parent or root, and suffix. So what goes into the prefix? The prefix is the first part. It tells you the position, the number of, and the name of substituents in the compound. Okay? Position, number, and name. That's one. Then we talk about the root. The root gives you an indication of how many carbon atoms you have in the longest carbon chain. Or in some books, they say longest continuous carbon chain. That gives you the root name or the parent name. Then the suffix tells you the homologous series. If it's an alkane, the name must end in "ane." If it is an alkene, the name must, so if it's an alkane, it must end in "ane." An alkene must end in "ene." Alkyne must end like this. An alcohol, all, and so on and so forth. I have already addressed that. But today's lesson is going to focus on only the rules for naming alkanes. When we are done with this, the next lesson we'll talk about how to name alkenes, alkynes, and the rest of them, because we'd have laid a very good foundation with the alkene. That's why it's always important to do a lot of examples with respect to alkenes, so that when you understand it, you can easily apply it to the other ones. It becomes easier. Okay? So we have the IUPAC rules for naming alkenes. The first rule is you must identify the functional group. The functional group. If it is an alkene, then it must be a hydrocarbon. A hydrocarbon means it should contain only carbon and hydrogen, okay? And it must also have what? Single bonds. So like this, like this. If you have something like this, this is ethane, like this, like this, like this. Okay? They are hydrocarbons. This is a hydrocarbon. This is called ethane. We have done that earlier on. Now, ethane has 2 carbon atoms and 6 hydrogen atoms. 1, 2, 3, 4, 5, 6. So the bond between one carbon and the other is a single bond, only one bond. So it is a hydrocarbon, and then the bond between one carbon atom and the other is a single bond. So that's how you're able to identify if something is an alkane. Okay, so that is one. Then the next step you do is to identify the longest carbon chain or the longest continuous carbon chain. Now, this gives you the idea of what we refer to as the parent or the root name. Okay, so if there's only one carbon atom, it is a meth, and then you add ane to it, so it becomes methane. Okay, if it is two, you say ethane. 3 propane, 4 butane, 5 pentane, 6 hexane, 7 heptane, and 8 octane, something like that. So you have that. Then we look at what we call the next rule is you identify what we refer to as side chains and count them. Now, anytime you have a structure, okay, a side chain is anything that is attached to the parent chain that is not hydrogen. So let me give you an example. We would look at more specific examples here, but let me just give you something like this. Okay, so this is a hydrogen, this is a hydrogen, this is hydrogen, hydrogen, and then here, let's say we write CH3. This is a hydrogen, this is a hydrogen, 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 hydrogen. So the longest chain is 1, 2, 3, 4. If you go like this, 1, 2, 3, 4. Okay, 1, 2, 3. So the longest chain is 4. So the longest continuous chain is 4 carbon atoms. So we can use this as our example. This is the longest chain. It contains 4. So 4 means it's a butane. 4 butane. Okay, 4 carbon atoms is butane. Now, any other atom or group of atoms that are not, or that is not hydrogen, we call it a side chain. So this is an example of a side chain. It's not part of the main structure. It's just an attachment, like what we call a side, I don't want to say side chick, but a side dish or whatever, if you have a DSTV at home, it is not part of the main structure. So this one is called a side chain, or it can also be called a substituent. Okay, so you have to count and name them, and then you choose the direction that is closest to the first substituent. So in counting this, you see, in this structure here, I could have counted 1, I can make this one 1, 2, 3, 4. And I can also count like this. So I can count going in this direction. 1, 2, 3, 4. Or I can count coming in this direction, which is 1, 2, 3, 4. Okay? So the rule is count in such a way that the substituent or the side chain has the least number. So if I count it from this from in this direction, it's going to be 1, 2, 3. It's attached to the third carbon atom. But if I count it like this, it's attached to the second carbon atom. 1, 2. So the direction of counting would be like this. So this methyl group is attached to the second carbon atom. Okay, not the third. Because if you count it in this way, it will be attached to the third one. But if you count it this way, it is attached to the second one. So that is how we use the one that has the least number. So we are counting from right to left. Then indicate the position of, that's what I've just explained. Then you use commas between numbers and then a hyphen between numbers and letters. I will show you what I'm talking about. Then for substituents, for the same substituents, if there are 2 of them, you use the word di. Di means 2. If there are 3 of them, you use tri. If there are 4 of them, you use tetra. If there are 5 of them, you use penta, and so on and so forth. So forth. Okay. Then you arrange them alphabetically. I hope this is clear. You arrange them alphabetically. That is how we name organic compound. Now, like we normally do, I always believe in giving specific examples so that you understand what we do. So this question says, give the IUPAC name of the following compound. The first step is identify the functional group. You look at it, you see that there are only carbons and hydrogen. Carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, all of them. There's no oxygen attached to it or nitrogen or fluorine. It's only carbon and hydrogen in this one. So this is an example of a hydrocarbon. But which hydrocarbon? The bonds, then you now look at the bonds. The bonds here are single bonds, single bonds, single bonds, single bonds, single bonds, single bond. So this is an alkane. If there was a double bond somewhere here, we say it is an alkene. If it's a triple bond, we say it's an alkyne. But because there's a double bond, I mean only single bonds throughout between the carbon atoms, it is an alkane, and therefore the name must end in ane, A-N-E, depending on the number of carbon atoms. So let me clean this like this. Okay. We are going to have it written like this. Okay. So we have identified that as an alkane. I've given the reasons already. So we say the suffix must end with ane. Okay. The suffix must end with ane. This one, A-N-E. Then we move on to what we try to identify what we call the longest continuous carbon chain. We identify the longest continuous carbon chain. So let's look at this, how to identify the longest continuous carbon chain using this molecule. Okay, so let's look at this. If we count it like this is carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5. So that is 5. But is it the longest continuous carbon chain? I don't think so. We can also count like this: carbon number 1, carbon number 2, carbon number 3, carbon number 4, and then carbon number 5, carbon number 6. So this is the longest continuous carbon chain from here, like this, like this. This is called the longest continuous carbon chain. Do you understand that? So you identify the longest continuous carbon chain, and if you identify the longest continuous carbon chain, it contains 6 carbon atoms. So it's a hexane. The name has to be a hexane because 6 carbon atoms is hex. Okay? Now, the other thing you should know is that I said anything that is not part of the parent structure, this is called the parent structure, is called a substituent. So this is a substituent. It's not attached to it. So this is a substituent like that. So you have to identify the substituent here, which is a methyl group. This is methyl, a methyl group. So that is the substituent, the methyl. Then you choose the direction. Now, we can count it like this. We counted it like this: 1, 2, 3, 4, 5, 6. We can also count it like this: 1, 2, 3, 4, 5, 6. So we can count it like this or backwards. Now, according to the rule, count it in the direction that gives you the smallest value of the position of the substituent. Now, this substituent, if you are counting it like this, coming like this, like this, like this, it's on carbon number 4. Okay, it's attached to carbon number 4. But if you are counting it from here, it's carbon number 1, carbon number 2, carbon number 3. So we are going to count it for this one because we want it to have the least number, the smallest number. So the direction of counting is going to be this. And therefore, our methyl group CH3 is attached to carbon number 3. This is 1, 2, 3. So it's attached to carbon number 3. So you are going to have, that's why I said, in this case, let me use this one as an example. This is a cleaner version, okay? This one is attached to carbon number 4 if we are coming in this direction. Because this is 1, 2, 3, 4. So this methyl group is attached to carbon number 4. But if we are going backwards like this, that is the case of this one. You see that it's attached to this methyl group. It's attached to carbon number 3. This is 1, 2, 1, 2, 3. So we use this one. This is the direction we are going to use. We are not going to use this direction. So according to this direction, the methyl group is attached to carbon number 3. So this is how we are going to write the name. I think I should just go forward and then write it without, because these other details may not be very necessary. They may not be applicable here. So it means that our methyl group, this one, is attached to carbon. Remember, this is 6 carbon atoms. When we counted them, the largest or the longest continuous carbon chain has 6 atoms. So the name must end in hexane. Okay? Then you have a methyl group attached to carbon number 3. So you write it like this: 3 methyl hexane. It means that your methyl group is attached to the 3rd carbon atom in the hexane. So this is the name, 3-methyl hexane. Now, the rule says that between numbers and letters, you use a dash or a hyphen. That's why this hyphen is there, to avoid confusion. So this is 3-methyl. The methyl is this group, a side chain that is attached to it, and then hexane is the longest continuous carbon chain. So that's how you do it, and then you get it. So having done this, now let's move to other examples, and see how we go about it. This one says, write down the IUPAC name for this organic compound, organic molecule. So we look for this one. We look at this one. This is carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5. Okay? So there are 5 carbon atoms if we count like this or like this. If we go like this, we're going to have 1, 2, 3, 4. So this one is 5. This one is 4. If we go in this direction, 1, 2, 3, 4. This is also 4. So these ones cannot be used. The longest continuous carbon chain has 5 carbon atoms. 1, 2, 3, 4, 5. So 5 is a pent or pentane. And since they are single bonds, it's a pentane. So we write here pentane. Then we try to find out what is attached to it. So this is the suffix. Remember I said the name, naming an alkane consists of 3 parts. We have the prefix, then the root or parent name, and then the suffix. The suffix is the homologous series or the homologous series of the functional group. In this case, it's an alkane. So this is a pentane. Okay? Pentane. So you are going to have that pentane there. You're going to have it like this. So this is a pentane. However, it is not just an ordinary pentane. There is something attached to the pentane. This is the longest continuous carbon chain here. And I said anything that is not part of the continuous carbon chain is a substituent. So this is a substituent. Now we have to identify the position of the substituent on this molecule or on this compound. So we are choosing this as our, so which direction do we choose? If we are going in this direction, it's going to be 1, 2, 3. So this substituent will be attached to carbon number 3. If you are going in this direction, going to be 1, 2, 3. So it doesn't matter which direction you choose because each of the direction gives you 3, position number 3. So we just use that. So your methyl group is attached to the 3rd carbon atom. So you write it like this: 3, position, and then dash. Then you write methyl, and then pentane. So this is the name of this molecule. Okay. Let's do some more. Let's come to this. Again, this is an alkane because there are only single bonds and hydrogen. So we try to identify the longest continuous carbon chain. The longest continuous carbon chain contains 1, 2, 3, 4, 5, 6. So this is this is the longest continuous carbon chain. If we use this one, this is going to be 1, 2 because there are 2 here. So 1, 2, 3, 4, 5, 6. So we can also use this one. Okay. So we can use this one or this direction. This one is 1, 2, 3, 4, 5. This one is short. So this is 6. 1, 2, 3, 4, 5, 6. So this is 6. If you count them in this way, we're also going to have 6 here. Okay. But when we go here, there are 5. So we will not choose this. We either choose this direction or that. Each one, any of them will be feasible. But for aesthetic purposes, to make things very easy for you, it's better to choose this one like this because it's straight and you can see it. So this is what we are going to choose. This is our longest continuous carbon chain, and it contains 6 carbon atoms. So 6 is a hex. So this is a hexane. Okay. Then we said anything that is attached to the the longest continuous carbon chain that is not part of the chain but is attached to it is a substituent. So this is our substituent, and this substituent is an ethyl. Remember I said there are 2 types of substituents, organic substituents that you should use. It's methyl and ethyl that you should know. This one is ethyl. I mentioned it earlier on. I don't want to go back, but maybe if you're interested, let me just go back. You see C2H5. When I was dealing with alkenes here, I spoke about, if you recall, yes. You see, I said alkyl groups. So ethyl C2H5, that is an alkane that has lost 1 hydrogen. So this is an ethyl group, or you can write it like this. It's also an ethyl group, ethyl. So that is an ethyl. And so we come back to it in we have, yeah, so this is, let me go forward. This is an ethyl. So this is ethyl. So this is our substituent, is ethyl. Now, which position do we choose? If we are going in this direction, it will be 1, 2, 3 to be on the 3rd carbon atom. But if we are going backwards like this, it will be on 1, 2, 3, 4. So we use the direction that gives it the smallest number or the smaller number. So 3 is the direction we are going to use. So this is on position number 3, carbon position. So it's going to be a 3 ethyl. So the molecule is going to be called 3-ethyl hexane, something like that. So this is the name of this molecule. Okay. Let's proceed with other examples. The more examples we deal with, the better you understand. So let's deal with this one. This one, the longest continuous carbon chain is 3. 1, 2, 3, or 1, 2, 3. So can be 1, 2, 3, or 1, 2, 3, or 1, 2, 3. Each direction you take is 3, is the highest. So 3 is a what? It's a propane. Okay? 3 is a propane. Propane. So if we are using this, let's assume this is what we are using as our longest chain, which is a prop. because it is 3. Okay. Then this one becomes a substituent, and this one also becomes a substituent. And they are on position number 2. Because if you count like this, 1, 2, 3 is on position number 2. Or if you count backwards like this, 1, 2, 3 is also on position number. But there are 2 of them. 2 of them. So there is on position number 2, we have a methyl. Okay. And on the same position number 2, we have another methyl. So there are 2 methyls on the same position. Now, I said if you have 2 of the same kind, let's go back and look at the rules. Let me go back here and look at the rules here. I said if there are 2, you use di. If there are 3, you use tri. If there are 4, you use tetra. So because there are 2 here, we are going to put di. Let me put. Yeah. So this is a propane. So we write propane here. Propane. Now, there are 2 methyls. So you say 2, I said between a number and a number, we use a comma. So 2, comma 2. They're all, and then dash. Then you use di to show that there are also 2 of them. This one shows their position. They are on carbon number 2. The first one is on carbon number 2, comma, and the other one is on carbon number 2. Now, between numbers and words, we use a dash, okay, or a hyphen. Now, because there are 2 methyls, we use di. So you say di methyl propane. So 2,2-dimethyl propane. That's the name. Let's continue. Then we come here. Again, we can identify the longest continuous carbon chain just by looking at this one. This is 1, 2, 3, 4, 5, 6. So this is, if we go like this or like that, there are 6 of them. 6. If we go like this, it's only 1, 2, 3. You can't use it. If we go like this, going to be, so like this, will be 1, 2, 3, 4, 5. This is 5. It's still small. If we go like this and come here, it's going to be 1, 2, 3, 4, 5. It's still small. So we cannot use this. We cannot use this direction. If you go here, 1, 2, 3, 4. It's even smaller. This is also smaller. So we can't use this. The longest one is this straight one. This one like this, going in this direction. Okay. So that is 6. Let me erase them so that it doesn't interfere with uh, our things. It doesn't interfere with our things. Okay. So that is 6. So this is going to be our longest continuous carbon chain is going to be this one. Okay. Longest continuous chain here. 1, 2, 3, 4, 5, 6. So 6 is a hexane. Hexane. I got them from the list of alkenes. Let me go back so that you see what I'm talking about in case you have forgotten. Remember this. Remember this, yes. This is not the one I'm looking for. Let me push it backwards. Yeah, let's even go to a better one. Yeah. So if it's an alkane, the first member, carbon number 1, if there's only one carbon atom, is a methane, 2 ethane, 3 propane, 4 butane, 5 pentane, 6 hexane, 7 heptane, and 8 octane. So those are where I get those names from. So you have to cram them. So let's come back to this one. So it is 6 carbon atom. So it is a hex. Hex. If you are forgetting, remember 6 has an X there. X here, hex. So sometimes you can use those things to remember. So this is a hexane. Okay. Now, any other thing which is not hydrogen that is attached to the longest continuous carbon chain is a substituent. So this is a substituent. We have to name them. This is another substituent. This is another substituent. We name them and then name the position. So in counting the numbers, we can count in this direction, or we can count in that direction. So this becomes 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. So I said you count in a direction where the first substituent is closer. If we count this one, it's going to be 1, 2, 3. On the third one, you have two substituents. But if you count in this direction, 1, 2 is on the second one. So the direction we are going to use is this side. So this is carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, carbon number 6. So that's the hexane. Then we have methyl. The first methyl is on carbon number 2. So this 2 methyl is this one, 2 methyl. Then there's another methyl on carbon number 4. So position 4, there is a methyl. Okay. And again, on position 4, there's another methyl. So position 4, there's another methyl. So there are 3 methyls, and therefore we say tri. Tri for 3. Tri is a tri-methyl. Okay. And the position is 2, 4, 4. So the actual name is 2, 4, 4 dash trimethyl hexane. So that's how you write the name. Okay, that's how you write the name. Then we go to the next one. The next one is also quite easy. When I look at this, I think with the experience that we have, this is the longest continuous carbon chain. So we take the longest continuous carbon chain as this one. 1, 2, 3, 4, 5, 6. So it's also a hexane. Hexane. So any other thing that is not hydrogen that is attached to the main chain or the parent chain is a substituent. So this is a substituent, this is a substituent, this is a substituent, this is also a substituent. Now we choose the direction. I said in numbering, you can choose either to go like this or to go like that. So you choose the direction where the first substituent is closest to the carbon atom. That's where you start your counting. If we are counting in this direction, this is carbon number 1, carbon number 2, carbon number 3. So on carbon number 3, we have 2 substituents. But if we are counting like this, it's going to be 1, 2. On carbon number 2, we start having the substituents, okay? So the direction we are going to choose is this direction. So it's going to be carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, carbon number 6. Okay? So on the basis of this, we are going to say that on carbon number 2, we have a methyl. So 2 dash, then we have a methyl. On carbon number 3, we have another methyl. So carbon number 3, we have a methyl. Then on carbon number 4, we have another methyl, this one. Okay. So carbon number 4, we have a methyl. And then on carbon number 4 again, we have an ethyl. This one is an ethyl. Okay. So also 4, then we have ethyl. So we have 3 methyls and 1 ethyl. However, according to the rule, you have to arrange them in alphabetical order. Remember this. That was the last rule here. Let me show you this rule. It says them arrange them in alphabetical order. Alphabetical order. So we come here. Yeah. So we come here. Now, in alphabetical order, E comes before M. A, B, C, D, E before you get to M. So we are going to start with this one. So the name is 4 dash ethyl. So we start with 4 and a dash ethyl. Then we'll put another dash there because there's always a dash between numbers and letters. And between numbers is a comma. So 4 ethyl, then we put a dash. And we have 3 methyls there. This is a methyl, this is a methyl, a methyl. So it's a trimethyl. But then the position must be indicated. Position number 2, position number 3, and position number 4. So it's put 2, comma, 3, comma, 4, then dash. Then you put trimethyl, then you bring this hexane here. Okay, hexane. So that is the name of this molecule. Continue with this one. Write down the IUPAC name of the organic molecule. Sometimes they draw it like this, with this structure like this. Again, if I look here, I can quickly realize that this is the longest continuous carbon chain. This is the longest continuous carbon chain going like this, like this, like this. This is the longest continuous carbon chain. So if we are numbering, we either number like this, go like this, okay? Can go like this, or we can number it like this. So the longest continuous carbon chain has 1, 2, 3, 4, 5, 6, 7, 8. So it's an octane. 8 is octane. Octane. Now, if you look carefully, anything that is not part of the longest continuous carbon chain is a substituent. So this is a substituent here, CH3, and this is also a substituent. It's also a CH3, just that it's in the form of the structural formula. It is not condensed like this, but that's why it's always important to use an ink or a pencil to identify the longest chain. See, the longest chain is this one. You see like this, it's like this. That is the longest chain. So this one is attached to the longest chain, okay? So it's an octane. Then let's look at the attachment. This is 1, 2, 3. If we are going in this direction, okay, it's 1, 2, 3. Then we have an attachment here. Here is also 1, 2, 3. We have an attachment. So it doesn't matter the direction we use. We will get the same thing because they are all attached to, they are the same things and they're attached to position number 3. So if we are going in this direction, this carbon number 1, carbon number 2, carbon number 3, 4, 5, 6. So on carbon number 3, you have a methyl. This one is on carbon number 3. And carbon number 6, you also have another methyl. So carbon number 3, we have a methyl. And then with respect to carbon number 6, we also have a what? A methyl. Okay, so the name will be 3, 6. So this is the position on 3, position on 6, but there are 2 methyls. So we say di. We put a dash here and put di methyl octane. So this is how the name is. Okay. So between numbers is a comma, between a number and a letter is a dash. Then you have that. So we come back to this, we come to this one too. It says what? Write down the IUPAC name of the organic molecule. So with this one, if I inspect it, I can see this is 1, 2, 3, 4, 5, 6, 7. So going this way is a 7. Okay. If we are going this way, it's 1, 2, 3, 4, 5, 6. This one is a 6. 6. So this is 7. This is 6. If we come here, 1, 2, 3, 4, 5, 6. Even this one here is also a 6. So the longest continuous carbon chain is this one like this. So let me clean this one and then we focus on that one. Okay? We focus on the longest continuous carbon chain. So this is the longest continuous carbon chain. This one, like this, going like this, like this, like this. This is the longest continuous carbon chain, okay? So we have a substituent here. Anything that is not part of the chain, that is not hydrogen, that is attached. So this is a methyl group. This is also a methyl CH3. This is an ethyl, okay? So how do we write it? So the longest continuous carbon chain has 7 atoms, carbon atoms. So this is 1, 2, 3, 4, 5, 6, 7. So a 7 is a heptane. 7 is a heptane. So 7 is a heptane. So we're going to put the parent name as a heptane. Then we look at the direction of counting. If we count in this direction, we're going to have 1, 2, 3. On the third, we have our first substituent here. In fact, 2 substituents. But if we're counting like this direction is 1, 2, 3, 4. So this direction is what we are going to use. So according to this direction, this is carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, carbon number 6, carbon number 7. So it's a heptane. So from 1, 2, 3, carbon number 3, we have a methyl. This is a methyl. Okay. And this, so this is a methyl. So there's a 3 methyl for this one. This whole structure is a methyl, just that is expanded or a structural formula. Then we have a methyl squeeze here, which is a condensed formula. So also on the same carbon number 3, there's another methyl. There's another methyl. And on carbon number 4, we have this one. This is an ethyl. I said the ethyl is written like this. Can either be CH2, C2H5, or it can be CH2CH3. So this is CH2 here. I don't know whether you can see it well. And this is CH3. So the ethyl is on carbon number 4. So 4, and there's ethyl, not methyl. So we arrange them alphabetically. What's happening? What's happening? What's happening? What's happening? Let me see. What is happening to my... Just wait. Yeah, okay. So we have that. Oh, it has frozen. It's not moving. So I think we should end the lesson here. We'll continue it later because I don't know what's happening here. But let me just try to see whether I can write a name so that we leave. So this is a 4-ethyl. So it's going to be 4-ethyl because E comes before M. Then a dash. There. Position number 3 has 2 methyls. So it's a 3, 3, and there are 2 of them, 2 methyls here. So we say dimethyl, and then you add your heptane. Let me see whether it's freezing. Okay, so ladies and gentlemen, my laptop is freezing. I don't know what is wrong with it. So let's end the lesson here. Let's end the lesson here and then continue the next time.